Hey, what's up, Algebra 2? It's Ryan. Today we're going to be going over the second part 2 of the radicals and rational exponents lecture. So far in part 1, we've talked about simplifying radicals as well as multiplying and adding radicals. But right now we're going to start with binomial examples where we do both. So let's just get started with that. So let's actually do number 16. So here, essentially, we're going to have to FOIL. So if we break this up into multiple parts, we first have to do this 8 times 3. So let's do that. And 8 times 3 is just going to be 24. Great. Not bad at all. And then we have to do, let's do negative root 10 times 3. That's going to be minus 3 root 10. And conversely, or similarly, we're going to do 8 times negative root 10. So that's going to give us minus 8 root 10. And then we're also going to have to do negative root 10 times negative root 10. Now, if I just said root 10 times root 10, let's start with that. Well, we can think of it as in two ways. One, we can think of it as root 10 squared, since we're multiplying it by itself. And these, the square root and the square, are sort of canceling each other out. So that gives us 10. We can also think of this as this is equal to square root 100 because we multiply 10 times 10. And that's just going to give us 10. Now, notice we have negative signs out in front. So when we multiply a negative times a negative, that's a positive. So we're going to add 10 to this. Okay, great. So let's add this 10 and this 24. We would get 34. And then we have minus 3 root 10 minus 8 root 10. So since we have the same radical with the same index, which is 2, since we don't see anything, it's just a normal square root, and the same radicand, 10, we're just going to do negative 3 minus 8, which we get minus 11. So we're going to say minus 11 root 10. And that is going to be, my bad. That's going to be sort of how we FOIL this out. Let's do number 18 too. So I find sometimes people find it easier if we write this out. So instead of saying 4 minus root 5 squared, just can sort of cross that out. Okay. We're going to just put another parentheses because as soon as we put that square sign, people sometimes get confused and forget to factor or forget to FOIL. So here again, let's do 4 times 4 and we get 16. Then we have negative root 5 times 4, we get minus 4 root 5. And then we have 4 times negative root 5 again, we get minus 4 root 5. And then we have negative root 5 times negative root 5. Now in this case, that's just going to give us, well, root 5 times root 5 is just going to be 5, sort of just like we did up here. So we're going to get 5, and then we have a negative times a negative, which is a positive, so we're going to add 5 from doing that. And so we get 16 plus 5, which is 21. And again, we have both of these terms. These red terms have square roots with the same index 2 and the same radicand. So we're just going to do negative 4 minus 4, which is negative 8. So we're going to do minus 8 root 5. And so a side note, if you're sort of confused on, maybe adding or subtracting these square roots, you can almost think of it, say we just subbed out this root 5 for y, and we had negative 4y minus 4y. If I asked you that question, you would say negative 8y, right? It's the same thing. We're just subbing a root 5 in for y. And so just as a note to keep important, if I said 4y minus 4x, you can't simplify that. So it's the same thing. They have to be the exact same thing. If they have a different index, which is that number that would go right here above or sort of right near this part of our radical, then if those numbers are different, then it's like saying y versus x. We can't add or subtract it. Same thing with radicands, and if they're different, which is the number under the square root. And here we have a question where we can essentially do the exact same thing. I'm not going to do it right now, but remember, area is length times width, and perimeter, we just add all this up and multiply by 2. So maybe try that. That's a good application question. Okay, so here we have dividing radicals. So we have the quotient rule. So when we have the nth root of a over the nth root of b, that's actually equal to the nth root of a over b. Okay? And we're going to use that in some of these problems. So first, I see 12 over 2. Instead of 12 over 2, I'm just going to write 6 over 1, which is just 6. So, you know what? I'll just put 6 over 1. You know what? Actually, let me start from the beginning. 12 over 2 is equal to 6. So I'm going to write 6. And instead of writing root 160 over root 5 by our quotient rule, which I just described up here, we can say square root of 160 over 5. Now 160 over 5, there's 25s and 100 and 12 5s and 60. So that's going to give us 32. So this is going to be equal to 6 root 32. Now we're not done. We need to simplify. So we think of some square root factors of 32. And the largest one is going to be 16. So I can rewrite this as 6 times square root of 16 times root 2. And square root of 16 is 4. So we're going to get 6 times 4 times root 2. 6 times 4 is 24. So we're going to say 24 root 2. And done. Okay. For number 4, we can do something similar. So first we have 28 over 4, which I can just rewrite as 7. And then we have root, or the third root of negative 16 over m to the 6th over the third root of 2m. So using our quotient rule, I'm going to write the third root of negative 16 m to the 6th over 2m. So I'm actually going to keep on writing this off to the side. So I'm going to keep the 7 on the outside, right? We're just going to keep that. But now we want to simplify this, what we have on the inside. So first we have negative 16 over 2. That's equal to negative 8. Okay? And then we have m to the 6th over m. Well, right, this m is basically m to the 1st. And if you remember, this was probably, this was a couple of lectures ago, a little while ago. We learned about some exponent rules. And that was if we have, for example, if we have a to the m, or that looks like a to the n, that works, over a to the m, oh Lord, a to the m, that's going to be the same thing as a to the n minus m power, right? We're just going to subtract the 2. So in this case, we do 6 minus 1, and that'd give us 5. So we have m to the 5th. Okay? So now what we want to do is we're going to say 7. And then what's the third root of negative 8? Well, that's going to be negative 2, because negative 2 times, maybe I should go like this, times negative 2 times negative 2 is going to be negative 8, right? Because negative 2 times negative 2 is 4. 4 times negative 2 is going to be negative 8. So this is like saying 7 times negative 2. And so we sort of got rid of this 8. And now we have to do the third root of m to the 5th. And so if you remember, I think before in part 1, I was talking about essentially you want to think about how many of these 3s, you want to look at the index. How many of these 3s can fit into 5 without going over? And that's only one. Only one group of 3s can fit into 5 without going over. So we're going to say times m to the 1st. And that m to the 1st is representing how many groups of 3s can go into 5 without going over. And then we ask ourselves how much is left over. And there's 2, right? When we only have one group of 3, that's 3. 5 minus 3 is 2. So we have 2 left over. So we're going to have to leave m squared, or m to the 2nd, under this radical. Okay? So something like that. And when we rewrite this, we have 7 times negative 2, which is equal to negative 14. And then we have m to the 1st, which is just m. And then we have the third root of m squared. And that's just going to be our answer. And that's a lot easier, a lot simpler than what we had in the beginning. Okay, so now we're going to talk about rationalizing the denominator. And this is a case when we're going to have to sort of apply the knowledge we've used before with multiplying and adding radicals. So essentially, the whole idea behind rationalizing the denominator is we might have a square root in the denominator. And it's convention in math to sort of stray away from that. We don't want square roots on the denominator. If they're on the top, that's fine. So we sort of want to ameliorate that problem and sort of get rid of that. And the way we do that is by sort of multiplying and picking specific numbers that can get rid of that square root. So first, let's talk about monomial denominators. That's when the denominator is just one term. So in this case, the denominator is just one term, 2 root 5. But if we have a plus or a minus, sort of like in number 15 or 16, 4 plus root 2 or 6 minus root 5, that is a binomial denominator. We have two terms. So when we have a monomial denominator, we want to multiply the numerator and denominator by the radical. And when we have a binomial denominator, we want to multiply the numerator and denominator by the conjugate, which is essentially just the same expression with the opposite sign in the middle. And we'll go over that. In a second. So let's first do number 9, which is an example of a monomial denominator. And so in this case, we have a root 5 on the bottom. So what we want to do is we want to multiply by root 5. Maybe I should zoom in a little more. Over root 5. And essentially what this does, or what we're doing here, is root 5 over root 5 is just equal to 1, right? Because they're the same value. And so by multiplying 3 over 2 root 5 by 1, we're not changing the value of this sort of fraction. However, we're changing how it's represented. We want to change it such that there's no square root on the denominator. So let's just go through this. We have 3 times root 5, which is just going to be 3 root 5. That's going to be our numerator. And then we have 2 times root 5 times root 5. And you know what, I'll write this out. Now, as I said before, we have root 5 times root 5. That's just going to equal 5. Okay, so this is the same thing as 2 times 5, which is just equal to 10. So we're going to have 3 root 5 over 10. Okay? And that's going to be our answer, and that's how we simplify that. And that's a lot easier and cleaner for us. Okay? Sorry. And then let's do something with a binomial denominator. Let's do 15. So in this case, our denominator is 4 plus root 2. So what we want to do, we want to multiply the numerator and denominator by the conjugate. So that means we're still going to have 4 and root 2, but now we're going to have a minus sign. And right, if you remember to before, this was a while back, but the whole point of conjugates is we're not going to have a middle term. We're going to have no b term, which, if you think about this in quadratics, because this kind of shows up in quadratics too. But you'll see, actually, once we solve this problem, you'll see what I'm saying. Okay, so we want to multiply by 4 minus root 2 over 4 minus root 2. Again, this fraction is equal to 1, so we're not really, we're not changing the value of this fraction. So we do 4 times 4, we get 16. And then we do 4 times negative root 2, and we get minus root 4 root 2. Okay, great. Now we do 4 times 4. That's equal to 6, or you know what? That's equal to 16. But let's actually write this out, because I'll explain what the whole point of multiplying by the conjugate. We have 4 plus root 2 times 4 minus root 2. Well, first, 4 times 4 is 16. So this is 16. And then we have 2 times 4, or root 2 times 4. So this is going to be plus 4 root 2. And then we have 4 times negative root 2. So we're going to say minus 4 root 2. And then finally we have root 2 times negative root 2, which is just going to be minus 2, since we have a minus sign. And root 2 times root 2 is just 2. You'll quickly notice that these two terms cancel out, because we have a plus 4 root 2 and a minus 4 root 2. And so you'll see we're left with just 16 minus 2, which is 14. And so we've gotten rid of this middle term with our root 2. And thus, we've gotten rid of the radical on the denominator. So let's rewrite this. Oops, okay, that's fine. As 16 over 4, or 16 minus 4 root 2 over 14. We can simplify this entire fraction by dividing every number by 2. So we end up getting 8 minus 2 root 2 over 7. And that's going to be our answer. Okay? Great. Now let's move on to rational exponents. So when we have a number a to the 1 over n power, that's going to be the same thing as the nth root of a. Sorry. And right, the nth root of a, it just means, and I've been saying this, if you look back before, when I say it out loud, that's the same thing as saying the nth root of a, like that, where we have a radical. And our index, we're putting our index, when we go from this radical form back to this exponential form, our index is being put under 1, and a is going to be our base. Okay? And so, sort of in the same vein, we have the nth root of a here, and let me start from the beginning. Here, for the second part, we have a to the m over n power. So we still have the nth root of a raised to the mth power. So I'm going to write, it's just like before, where we have n as our index and a there. But I'm going to raise a to the mth power there, like that. Because essentially what this is doing is it's saying, right, we're a to the m over n power is equal to a to the m times 1 over n. Now a to the 1 over nth power is just this, and then we have to raise it to the mth there, if that makes sense. Okay, let's just put this into practice and hopefully it'll make more sense. Okay, so first we have x to the 1 over 4th power. Well, what's n equal to in this case? N is equal to 4, and in this case our a value is just x. So we can rewrite this as the 4th root, where n is our index, and x is going to be under a radical, something like that. Okay? Here we have 15n raised to the 1/2 power. So n is equal to 2. And 15n is going to be our a value. So this is going to be the square root, where I don't have to write an index because it's assumed it's 2 of 15n. So you'll notice that raising something to the 1/2 power is the same thing as taking the square root. Okay? Now we have 24 raised to the 1/3 power. N is equal to 3, since we're just taking that denominator. So we're saying the 3rd root of 24. And they're saying simplify if needed. Let's think about some perfect cubes. We have 8 as one of them because 2 times 2 times 2. So we can say this is equal to 2 the cube root of 3 because, sorry, let me just explain this real quick. The cube root of 24 is equal to the cube root of 8 times the cube root of 3, because 8 times 3 is 24, and we just said the cube root of 8 is 2. So that's how we get that. So if you're just looking across here, you'll see that if we go the other way, if we go from the fourth root of x to exponential form, you'll see that we're just putting our index over or under 1 and just putting that as our exponent. Okay? Again, these are the same thing. Sometimes it might just be easier to, when you're solving something, maybe it's easier to have it in exponential form where you have a fractional exponent. But typically in your answers, I think it's more common to write it in this radical form, something like this. Okay, so let's do some examples like k to the 7 over 2 power. In this case, we have an example that resembles a to the m over nth power, where m is equal to 7 and n is equal to 2. So we're going to say the square root, right, where we would have a 2 here. We sort of have an invisible 2 right here, to the k to the 7th power. Okay? Great. Because essentially, I mean, what you can think of k to the 7 over 2 power as being, that's equal to k to the 7th times 1/2. Okay? Right? Because 7/2 is just equal to 7 times 1/2. And if you remember, sort of working backwards, if we multiply these, that's going to be equal to k to the 7th all to the 1/2 power. And you know how I just said raising something to the 1/2 power is equal to taking the square root of it. From there, we can get to the square root of k to the 7th. Okay, great. So let's, for pretty much all of these, it's just going to be the exact same thing. Same principles apply, even if it's negative or such. Okay, so now we're going to work the other way. We have this in radical form, and we need to write it in exponential form. So we want to look at our n value, which is our index, and we see in this case that it's equal to 3. So we're going to say 16 to the 1 over n, or 1 over 3 power. In this case, we can't see an index, so we assume it's 2. So we say n is equal to 2. So we have x, y. I'm putting in parentheses just to make sure. We raise it to the 1 over nth power, which is just equal to 1 over 2. Okay, so in this case, we see the fourth root of k to the 5th. N is equal to 4. M is equal to 5. So we say it's equal to k to the 5th over to the m over nth power, so 5 over 4th power. So something like that. Okay, great. So now let's talk about simplifying expressions with rational exponents. For these types of problems, we want to rewrite all radicals in exponential form, and then we just use exponent rules to simplify the expression. So essentially, right, our exponent rules in number 19, we have x to the 1/3 times x to the 4/3. Our exponent rules tell us if we have the same base, x, and we're multiplying those, this is going to be equal to x to the 1/3 plus 4/3. Okay, 1/3 plus 4/3, we have the same denominator, so we just do 1 plus 4, which is equal to 5. So that's going to be equal to x to the 5/3. And now we want to rewrite this as a radical in simplest form. So we have m is equal to 5, right? Our numerator of our exponent, n is equal to 3. So this is going to be the same thing as the third root, n is our index, as the third root of x to the 5th. Okay, something like that. Now, let's do something like 22. So this is going to be equal to a, right? When we raise an exponential form, something in exponential form to another exponent, we multiply the two. So in this case, we do 1/3 times 5/2, and that's equal to a to the 5th over 6, right? Because we just multiply across. We do 1 times 5 is 5, 3 over 3 times 2 is 6. And now we just need to rewrite this in radical form. And we see that our denominator, we want to put our denominator as an index, 6. We have our base a, and then we just raise our base to our numerator, 5. Okay, great. Now let's do something like, let's do this case. We have negative 216 raised to the negative 1/3 power. Now this can be tricky because we're introducing negatives. So let's rewrite this equation. We have, since we have a negative exponent, I can rewrite this as 1 over negative 216 to the 1/3 power. Because when we have a negative exponent, a to the negative nth power is equal to 1 over a to the nth power. Okay? So now it's just a matter of, and I should probably put parentheses around this. Now it's just a matter of raising negative 216 to the 1/3 power. So I guess maybe it's best for us to write this as 1 over the, we have our denominator is 3, so we're taking the third root. That denominator becomes our index. We have the third root of negative 216. Now, if you think back to perfect cubes of 216, that's going to be 6, which comes out perfectly evenly. So the cube root of 216 is 6, but we have this negative out in front. And since we have an odd root, 3, we have an odd index, that matters. So we can say the third root of negative 216 is actually going to be equal to negative 6, because negative 6 times negative 6 times negative 6, this is equal to 36, and then we still have this last negative 6, and that gets us to negative 216. So I can rewrite this as 1 over, and since we said the third root of negative 216 is equal to negative 6, I can say negative 1 over 6, and simplify it a lot just by doing that. Let's just do number 29. Since these, I think it's important to get a lot of practice doing and being very fluent in these, because especially once you get to calc, you're gonna have to, change your exponents a lot and simplify and move very quickly. It's gonna be expected of you that you can do this stuff really fast and without problem. So it's really important we master this. Okay, so in this case we have a third root. We're taking the third root of v and multiplying it by the square root of v. So I'm going to rewrite this in exponential form. this is equal to v to the 1/3 power, right? We just make that index 3 our denominator of our exponent, and we multiply that by v to the 1/2 power, right? We have an invisible 2, and so we make that index the denominator of our exponent. Now, since we're multiplying to sort of exponential v to the 1/3 and v to the 1/2 with the same base v, we add these exponents. So we do v to the 1/3 plus 1/2. Now 1/3 is equal to 3/6, or sorry, 2/6. I was getting the other two mixed up. 2/6 plus 1/2 is equal to 3/6. So we just add these together, we get 5/6. So this is equal to v to the 5/6. And we can rewrite that with the 6th root, where we make our denominator our index of v to the 5th. Okay, perfect. Now, I think that's it for today. So if you have any questions with how I did any of these problems, please go to your teacher or go to the tutoring center, and definitely feel free to reach out to me. I'm always happy to help. And also, of course, use the internet, use your peers, use upperclassmen, other people you know, maybe siblings who know this pretty well. So yeah, thank you, and have a nice day. Bye.